So last time we did bed mass for chapter 2, and now we're going to start with 2.1, which is the more formal part of chapter 2. Bed mass is just something that's kind of off to the side, although it is on the assignment. So we'll start with 2.1. Just a reminder, the assignment number 2 is up online on D2L. It has no due date yet. Again, once we finish the chapter, then we'll decide on the due date, but it's just up there in case anyone wants to work on it early. So let's share screen. And no pets today because I'm stuck at the school today. Although sometimes I do bring Buddy into the school and people seem to like him. Okay, good. So 2.1, ratios and proportions. So we start off with a bit of a side note regarding multiplication. So the standard symbol for multiplication is of course the multiplication sign, but it's not a great sign to use. Mathematicians generally don't use it because it could be easily confused with the letter X, and the letter X is primarily what you use when you're doing algebra. And algebra can get complicated. Like, I'm sure there are algebraic proofs and algebraic problems that literally go on for hundreds of pages. I think I heard that there's technically a proof that's 10,000 pages, I think for group theory. So we obviously won't be going the 10,000 page route, but it's just a side note that, yeah, the multiplication sign, it's not a great sign because it could be easily confused with X, especially when you're doing more complicated math. So here are a couple of options for alternate signs. Not too big of a deal. It's just, again, it's just a side note. So let's say we have A times B. A times B. Actually, hold on, let me fix my writing. That's better. So if you don't want to use the multiplication sign, you could just do A dot B with a dot between them, and that automatically depicts multiplication. You could use brackets. You could just do A times B like that, and that also depicts multiplication. Or you could use nothing at all if it doesn't lead to any ambiguity. So if you have, in this case, you could just write A, B, and that's automatically counts as A times B. It kind of goes without saying. Obviously, you can't do that if you have like entirely numbers. If you have numbers, then you got to use like a dot or the brackets. So those are just some alternate uses that you can use instead of the multiplication sign. Although ironically, I do use the multiplication sign in this lesson. So I do feel like a bit of a hypocrite, but oh well. Okay, so before we start on ratios and proportions, we're going to learn some basic algebra, how to solve some basic algebraic equations. And there's the multiplication sign right there. Apologies. So here is the question. A number multiplied by 40 gives us 2,200. And we have to find out what is this number. So what we can do is we could set it up as an equation. So 40 times some mystery number equals 2,200. So we can set that up like this. So 40 times n, where n is our unknown number, and that equals 2,200. So there's the initial equation that we have set up for this, and now we're going to learn a maneuver to get n by itself. So basically what you can do is, so we want to get n by itself, so we want to get rid of this 40, but we have to do it in a fair way. Like, you can't just cross out the 40 and that's it, because then you're changing the equation. So what you can do is you can, there's kind of two different ways of looking at this. Actually, let's go to a whiteboard for a second, just for illustration. So 40 times n equals 220. Okay, 40 times n equals 2,200. So one way of doing this is you could divide each side by 40. So that'll cancel out the 40 next to the n, and then you'll get n by itself. And you're treating each side equally, so you still maintain the same equation. So you could do that. You could do divide by 40, and again, your goal is just to get n by itself. And in this case, the two 40s on the left would cancel each other out, so that's good. And then you would get n equals 2,200 divided by 40, which is something. It's like, I can't remember. Let's see what it is. Someone says 55. That sounds right. Very good. 55. So you could use this method where you divide each side by a particular number, whatever number you have to get the variable by itself. But I don't like this method very much. At least I don't like the way it's formatted and presented, because you're temporarily cluttering up your equation by putting more numbers in there initially. Like we got this 40, we got this 40, and then we got a bunch of other stuff. So I don't like the format that this uses. So there is thankfully a more convenient trick that you can use that is the equivalent of what we just did right here. So now I'm going to show you that trick. So let's just write the original equation. 40 times n equals 2200. So the trick is, if you want to get rid of something, you can move it from one side of the equation to the other, as long as you give it the opposite operation compared to what it had before. So if you want to get rid of this 40, and in this case, you have 40 times n, what you can do is you could just take the 40 and move it to the other side and change it to division. And that's the equivalent of what we did a few seconds ago, except this way you don't clutter up your equation by inserting a bunch of stuff into it. You can literally just move stuff around like a puzzle piece, as long as you do it properly. So in this case, again, just picture the 40 going from this side to this side, and then when it gets on the right side, it switches from multiplication to division. And you get n equals 2200 divided by 40, which is 55. So that's the method that we'll be using in general. So you can switch stuff around in an equation. You just have to remember that if it's multiplication on one side and you switch it to the other side, you have to change it to division, and vice versa, because multiplication and division are opposing concepts. So here I'll just write multiplication and division. Those are always paired together like that. And then if you had plus on one side and you moved a number to the other side, you would change it to minus and vice versa. In this case, we don't have to worry about that because these equations, it's all just multiplication and division. They're very, very limited. So let's look at this trick again. Let's just go back to the PowerPoint. Okay, so let's look at a similar one, and we'll just directly use this new trick. Okay, so we got 25n equals 275. So 25n equals 275. And our goal is always getting the variable by itself. So you just want to move whatever is next to the variable to the other side just to get rid of it, so the variable is alone. So it's 25 times n in this case, so just take 25, move it over, put it on the bottom, and that changes it to division. So n is going to be 275 divided by 25. And that is, I think that's 11. Yeah, that'll be 8 plus 3, 11. So in this case, n is equal to 11. And these are pretty easy to check. If you wanted to, you could just reinsert 11 into the original equation, and you'll see that 25 times 11 indeed equals what it should equal. It does equal 275. So yeah, I like this trick better than like visually dividing by each side, because again, it avoids all the clutter of doing that, and it's still the equivalent of doing that. So it's a good trick. Let's see if we have anything else. And I'll just read this. So this example illustrates an important trick. Notice that we have 25 on the left side, and we're allowed to switch it to the right side as long as we put it on the bottom. And in that case, we're technically just dividing each side by 25, except we're doing it in a more streamlined way. And here's another one, pretty much the same thing. So you got 100, x equals 550. And you want to get x by itself. In this case, x is just a variable. So you take the 100, move it over, and same thing, just put on the bottom on the other side. So x is equal to 550 divided by 100, which should be 5.5. So that is the basic trick for dealing with algebraic expressions, and we'll be using that later in the algebra chapter as well. Let's see what else we have. This one is pretty much the same, although some people make a mistake with this one because the variable is on the right side instead of the left side. But logically, it doesn't make any difference. So 15 equals 30a. So in this case, a lot of students don't know which number to move. And just remember that the number that you move is just whatever is sitting next to the variable. So 30 is sitting next to the variable in this case. So that's what you move because you want to get the variable by itself. So that's the rule for remembering which number do I actually move. So you just take the 30 and you want to get rid of it. So take it and move it and put it on the bottom on the other side. And you get A is 15 divided by 30. And then that equals 0.5. So A in this case is 0.5 or 1/2. And again, if you plug that into the equation, it actually does work, despite the fact that it's a decimal number. Because if you plugged it in right here, you would get 30 times 0.5, which indeed does equal 15. So yeah, for some reason, people get stuck on that one. But again, just remember, you're just moving whatever is sitting next to the variable. And that tells you what number to move to the other side. What else? And this is the trick. If the number is on top, we could switch it to the other side and put it on the bottom. If a number is on the bottom, we could switch it to the other side and put it on top. And of course, the bottom is referring to division, and on top, it's always implied to be multiplication. So those are some basic, or one basic rule for algebra. And algebra actually has a really, really fascinating history behind it. I can't remember if I told this to you. I think I told this to another class. So here I'll go on a bit of a rant. Yeah, so everyone might remember that in high school you did quadratic equations, and then you had that fancy quadratic formula as well. So let's just go to a whiteboard, and this is just going to be a bit of an offshoot. I'm just going to talk about the history of solving equations, because it's a very interesting history, and there's some funny stuff in the history as well. Like there's one mathematician that I'm going to talk about who has a really, I know it sounds really cold when I say this, but he has a really hilarious death. There's so many funny mathematician deaths throughout history. And again, I'm allowed to say that because all these their relatives are all gone anyways. Hold on, I'm just trying to find the wiki page of this person, but his name is hard to spell. Let's see, hold on. I'm just going to type in group theory because he invented group theory. Where's his name? Yeah, it's a mathematician called Galois, but I just can't remember how to spell this gosh darn name. Okay, let me Google this. Apologies. Group theory, French mathematician. There, I'm getting really desperate. French mathematician. There he is. There he is. Okay, I found his Wikipedia page. Okay, so anyways, okay, so remember in high school you had the quadratic equation. You had something like, and we're not even going to be covering anything this advanced, so don't worry. It was an equation that looked like this. It was ax squared plus bx plus c equals 0. That was typically what the quadratic equation looked like. The quadratic equation is just something that has an x squared in it. And then of course they found a formula. It was the quadratic formula. Everyone at least kind of like recalls that there was a formula for this in high school. So at one point they figured that out, and then they tried to move on to the cubic equation. And so the cubic equation would be in the form ax to the 3 plus bx to the 2 plus cx plus d equals 0. So the cubic equation would just be an equation that has an x to the 3 in it. And then at one point they did indeed figure out the formula for the cubic equation. It's a little longer than the quadratic equation, but it is kind of a convenient closed formula that will give you the answer to the cubic equation. And then they kept going. They eventually found a formula for the, I guess you would call it the quartic equation, which is an equation that has an x to the 4. But then when it got to time to try to solve the x to the 5 equation, the quintic equation, they got stuck for a really, really, really long time. It might even been like decades or maybe even hundreds of years that all these mathematicians are trying to figure out, does the quartic equation have a nice formula that will tell you what the solution is to the equation? And then in one of the most stunning upsets in math history, a 20-year-old proved that there is no formula for the quartic equation. So it was one of the first times in math history where someone proved that the solution to the problem was that there was no solution to the problem, and that there is no nice closed form equation for the quartic equation. So that stunned a lot of people. And for some reason, it was solved by two people at the same time, both very young people. One was Galois, a French mathematician who died when he was 20. So I guess he did that before he was 20. And then another one was Abel, who died when he was 27. They both simultaneously proved what hundreds of mathematicians hadn't been able to figure out, that there is no solution to what they were looking for. So that was really, really, really surprising to some people. And the fact that it was solved by a 20-year-old. And this 20-year-old Galois, he has a hilarious Wikipedia page, because basically he was like one of the great geniuses in history. And then he got in a duel over a girl and he died when he was 20. So it was like a very, very unglorious death for such a stunningly intelligent person. And he did a lot of important work before he died. I can't believe that he did this before he was 20. That's unbelievable. Just for fun, let's look at Galois' Wikipedia page, and then we'll continue on with the lesson. But I'm always entertained by all the funny mathematician deaths that we have throughout history. Let me just bring this up, and we'll see what his Wikipedia page says. Wikipedia. EVARISTE There we go. And let me just share this. Okay, share screen. Here he is. So here is Galois. I don't even know how to pronounce his first name. I'm not good at pronouncing things. So yeah, was a French mathematician and political activist. While still in his teens, he was able to determine the necessary and sufficient condition for a polynomial to be solvable by radicals, thereby solving a problem standing for 350 years. So this teenager was able to solve stuff that the greatest minds in history couldn't figure out for 350 years. That's one of the fascinating things I find about mathematics, is that you have some people who don't even have much of an education, like the Indian mathematician Ramanujan, who I think dropped out of university because he failed a lot of his classes. And he created all these crazy mathematical theorems. He started creating them when he was like 12 years old. He was even mentioned in Good Will Hunting, which is a pretty good movie. Let's see. So Galois, his work laid the foundations for Galois theory and group theory, which I studied in university. So yeah, and then died at the age of 20 from wounds suffered in a duel. You don't hear that very often anymore. It seems not many duels going on around this time. And here, there's an interesting quote about him. Let's see. There's a quote about how intelligent his contributions were to mathematics. Apparently, people were pretty impressed with his contribution. Where is that quote? I've read it on here before. Let's see. And we have a bunch of quotes before his death. Yeah, I don't know if it's listed here, but basically one mathematician said that even dying at the age of 20, he still left behind enough material to keep people busy for the next 500 years. That was the depth of his intelligence and the math that he created, that it would take people hundreds of years to fully appreciate it and decipher it. So very interesting history behind equations, but unfortunately we won't be looking at anything so complicated. Anyways, let's continue on with the lesson. Okay, so we've come up with this nice little rule for rearranging algebraic equations. So we have to keep that in our back pocket for now. Now let's look at ratios and proportions, and then eventually when we have to solve some proportions, we'll use this trick. Okay, so we use ratios to make comparisons between things that are measured in the same units. So a ratio is just comparing two things. So there's various ways you can denote a ratio. You can write it as a fraction, you can use a colon, or you can just use words. So here's an example. Let's say we are comparing 10 milliliters or 1 milliliter to 10 milliliters. So as a fraction, you can write it like this. Using a colon, you can write it 1 colon 10, or you can just write it as 1 to 10. In our case, we're just going to be using fractions because the latter two ways of writing this are not great ways because you can't really do any math with them. Like it'd be really hard to do math with this one especially. And this one would be difficult as well. You'd have to like kind of recontextualize it and just kind of picture it as a fraction, which is kind of pointless when you could just use the fraction. So in other words, we're kind of regressing back to fractions because it's the most convenient way of denoting a ratio. Okay, let's see. Oh, and make sure you set up your ratio in the correct order. So for example, let's say you have a ratio 3 to 17. So in this case, if you want to write it as a fraction, the correct way is 3 over 17. So the first number will be on top and the second number will be on the bottom. If you write it in the reverse way, it will not be correct. What else? What else? Okay, so that's is that all for ratios? Okay, that's all for ratios. And now we look at the definition of a proportion. So a proportion is a statement that two ratios are equal. So the numbers that make up the two ratios will be different, but their relative values will be the same. Now here is an example of a proportion. And it's a pretty straightforward example. So you got 1 over 3 is equal to 4 over 12. So it's a comparison between two ratios. And in this case, of course, this is a true proportion because like 4 over 12, we already know that it reduces to 1 over 3. So it's obviously a true statement. Indeed, 4 over 12 does equal 1 over 3. And you could write this in various ways. You could write it with a colon, which would be 1 compared to 3 equals 4 compared to 12. So they both have the same relative value. They both have the same size when you compare each of them to each other. Or you could write it 1 is to 3 as 12 is to 1 is to 3 as 4 is to 12. But that right there kind of illustrates why you would never really want to use sentences or words for proportions. It's way better just to use fractions. So that's an example of a proportion. Now with proportions, what we're mainly going to be doing is you'll be given a proportion and one of the numbers will be unknown. It'll be just a variable. And it's your goal to rearrange the proportion to get that variable by itself to figure out what it's equal to. And then you could finally establish what the full proportion is. So let's look at one of those. So here is an example. Solve for x given that, let's write this down. Okay, x over 4 is equal to 12 over 16. And it's our job to figure out what is this x value that would make this proportion true. Now, a lot of these are pretty easy to solve just by observation or just by using some of the skills that we developed in chapter 1. Like for example, you could take 12 over 16 and reduce it to 3 over 4. And that makes it kind of clear that x is just going to be 3. So that's one way of doing it, but that's not a very reliable way of doing it. So what we're going to do is we're going to use algebra to solve this. In other words, we're going to rearrange this to get x by itself. This particular example is the easiest type of example because you have the variable on top, you have a number below it, and all you have to do is just move that one number to the other side. And of course, you have to do it properly using our special algebra technique. So in this case, we want to get x by itself. So let's just take this 4 and move it over. And since it's on the bottom, you just move it over and switch it to the top and change it to multiplication. Remember, division changes to multiplication and vice versa. So what you get is x equals, so the 4 just joins the 12 at the top and becomes multiplication. And the 16 just sits there at the bottom. So 4 times 12 is 48. And then 48 divided by 16 is equal to 3. So for your answer, you would say, therefore, x is equal to 3. Or what you could do is you could write the full proportion. That would also be an acceptable answer. You could say, therefore, 3 over 4 is equal to 12 over 16. And in this case, you have indeed solved for your unknown variable. So that's basically what we do in this chapter, just rearranging proportions to figure out the whole thing. And like I said, this is the easiest type of proportion because the x is just on top and there's not much to worry about. You just have to do one of these maneuvers, but you might have more, slightly more complicated ones. So we've just done this one. Okay, so let's look at another one that's a little more difficult. So this one is 6 over n equals 15 over 10. So let's write that down. So this one throws a lot of people off because the variable is on the bottom. So when I ask people like, which number should you move first? What should you do? Most people say move the 6, but that's not really going to help because the n will still be stuck on the bottom, even if you move the 6 over to the top. So this one's a bit of a tough one. So what you do is basically you can't solve this as long as the variable is on the bottom. So the first thing you do is just move the variable, and you can move it just the same as you move numbers. So what you do is you take the n and just move it to the other side and switch it from the bottom to the top. And then at least you have the n on top where eventually you can actually solve for it. So in this case, when the variable happens to be on the bottom, the variable itself is the first thing that you move over. So let's see what we get. So the 6 will just sit there. So we get 15 n n's on top over 10. Okay, so that's what we get so far. So yeah, n just joins the 15, everything else is the same, good, good. And then we just have to do a couple of other maneuvers in order to get n by itself. We have to get rid of the 15, and we have to get rid of the 10. You could do this one at a time, or you could kind of do both of them at the same time if you want. You could picture the 10 going to the other side and moving to the top, and you could picture the 15 moving to the other side and moving to the bottom. So again, you could do them one at a time or both at the same time. It just depends on what you feel like doing. So let's just do them both because it doesn't really matter which one you move. So picture the 10 joining the 6. So 6 times 10, and picture the 15 going on to the bottom, and there it is. So the one where the variable happens to be on the bottom is definitely the more difficult one. In a couple minutes, we'll look at a slightly better type of solution for solving these kinds of problems that people seem to prefer. So anyways, this will be 60 over 15, and 60 divided by 15 gives you 4. So therefore, n is equal to 4. Oh, and this symbol right here with these 3 dots, that just means therefore. That's a therefore statement where you just state your final answer. I do like therefore statements on the assignments and the tests because it makes them way easier to mark. Usually I'll check your therefore statement. I'll see if it's correct. I'll check to make sure that you did some reasonable amount of work, and then I move on, and it usually takes about 2 seconds per question. So try to include therefore statements or highlight your answers because it just makes it easier to mark. So for this one, let's try a slightly different, there's a trick we can use with this one that really skips a couple of steps and makes it a lot easier. So let's just go to a whiteboard for this. Just hold on, let me catch up on my laptop. 6 over n. Okay, new share, whiteboard, get rid of this. 6 over n. So same question, 6 over n is equal to 15 over 10. Okay, so here is another trick that you can use. What you can do is you could flip each side upside down. You can invert each fraction as long as you do it on each side. And that makes it a lot easier to solve. So you literally just flip this one like this and flip this one like this. So on the left side, you'll get n over 6. And on the right side, you'll get 10 over 15. So that's a really, really nice trick because like now you have the variable on the top, and all you have to do is just move the 6 and you're good to go. So that's one trick you should keep in mind. I can't remember what it's called or if it even has a name, but in general, you can invert each fraction on each side as long as you just invert both of them because it ends up being the same thing. And then in this case, you just take the 6 and move it over and switch it from the bottom to the top. And you get the same answer. You get 10 times 6 over 15, which is 60 over 15, which is 4. So same answer regardless. So most students prefer this method because you just flip them and then it's basically reduced to the simpler version of the equation where you just have to move one thing. Let's see, and there is another PowerPoint online called Solving Proportions, More Examples, and it's exactly what it sounds like. It's just more examples of solving proportions. Someone requested it, so I wrote it. Although there's really only 2 cases in here. There's just the case where the variable's on top or on the bottom, so there's really not much variability to these questions in the first place. Let's see what else we have. Let's do one more where we have the variable on the bottom. So this one is, and I'd recommend that everyone try these on your own and see if you end up getting the same answer. So 12 over y equals 8 over 50. And some of these you could like kind of guess the answer or kind of roughly guess the answer. Like 50 is a lot more than 8. So the answer y should be a lot more than 12, according to the same proportion. Actually, if you took 8 and multiplied it by 1.5, that would get you to 12. So technically, you could just take 50 and multiply it by 1.5, and that would get you 75, which is the correct answer. So there's like lots of little tricks that you can use, or maybe I just use them, I don't know. But we do have to still have an algebraic solution for these. So we still have to solve them formally, even if a lot of them, we could kind of use some guesswork. So in this case, we want to solve for y. So let's just do the easiest trick. Let's just flip both sides upside down. So we get y over 12, and we get 50 over 8. Good, and now last step, pretty straightforward. Just take the 12 and move that to the other side and change it to multiplication. There we go. So we get y is equal to 50 times 12 over 8. Which is 600 over 8, and 600 divided by 8 is 75. So let's just put that in the proportion, and let's just see if it looks reasonable. So 12 over 75 equals 8 over 50. That seems reasonable to me because the bottom is larger than the top for each of the sides, and it seems to be the same proportion. So yeah, I'm satisfied that that's correct. Does anyone have any questions? So the rest of this is application problems, where you're solving word problems, kind of more related to the medical fields, but we don't really have time to start on these. So I guess this is a good time to stop. Okay, so at least that was, okay, it's 12:06, at least that was a semi-solid lesson. Okay, so again, does anyone have any questions? Oh, let me, as you're doing that, let me just take the attendance. I have almost all of it. We have this person, and I think I have this person. And this person. Oh, I forgot this person. Pretty much everyone is here. And good. Okay. Said everyone, yes. Okay, so I guess that's it for today. So we'll continue with chapter 2 on Friday, and you can start working on the assignment if you want. So if no one has any questions, that's everything, and have an awesome day. Bye.
Thank you.
No problem.
I have a question.